Hello everyone. Today we will discuss about module 4 of IoT and wireless sensor networks. This module 4 that I have divided into 8 sessions and this is the first session. In this session 1, we will discuss about challenges for wireless sensor networks and enabling technologies for wireless sensor networks. First, we will discuss about what are the characteristic requirements that are needed for wireless sensor networks. First requirement is type of service of WSN. In conventional type of network, we were just moving the bits from one place to another place. But in wireless sensor network, we are not concentrating to move the bits from one place to another place, rather than we are expecting the answers. That means that for particular nodes, particular task will be given, and that particular task that will be performed by the nodes, and that performed after performing that particular task, so that information that will be given to the sink. So actual information, the meaningful information that is needed for wireless sensor network, rather than simply moving the bits across the network. The second characteristic is the quality of service. Traditional quality of service metric do not apply in wireless sensor networks. In some cases, only occasional delivery of a packet can be more than enough. In other cases, very high reliability requirements exist. In yet other cases, delay is important. So the packet delivery ratio is an insufficient metric. What is relevant is the amount and quality of information that can be extracted at given sinks about the observed objects or area. Next, coming to the fault tolerance. So the network must be robust against node failures. So to overcome from the node failures, we are going to use the redundant nodes. There is a chance of nodes may run out of energy or might be damaged. Or since the wireless communication between two nodes can be permanently interrupted, it is important that the WSN must tolerate such faults. So for that, to tolerate node failures, we are going to deploy the redundant nodes. Using more nodes, so we can, if the one node fails, another node will take up that work and it will perform according to the task that is given. Next characteristic is lifetime. The precise definition of lifetime depends on the application at hand. A simple option is to use the time until the first node fails as the network lifetime. Other options include the time until the network is disconnected in 2 or more partitions, the time until 50% of nodes have failed, or the time when for the first time a point in the observed region is no longer covered by at least a single sensor node. Network should fulfill its task as long as possible, and the lifetime of individual nodes are relatively, that is, unimportant, but often treated equivalently. Next characteristic is scalability. The network support large number of nodes. Since a WSN might include a large number of nodes, the employed architectures and protocols must be able scale to these large numbers. Wide range of densities. In a WSN, the number of nodes per unit area, that is the density of the network, can vary considerably. Different applications will have very different node densities. Even within a given application, density can vary over time and space because nodes fail or move. The density also does not have to be homogeneous in the entire network, and the network should adapt to such variations. The next characteristic is programmability. Not only will it be necessary for the nodes to process information, but also they will have to react flexibly on changes in their tasks. These nodes should be programmable and their programming must be changeable during operation when new tasks become important. A fixed way of information processing is insufficient. The next characteristic is maintainability. As both the environment of a WSN and the WSN itself change, that is depleted batteries, failing nodes, a new task, the system has to adapt to those. It has to monitor its own health and status to change operational parameters or to choose different trade-offs. For example, to provide lower quality when energy resource become scarce. In this sense, the network has to maintain itself. It could also be able to interact with external maintenance mechanisms to ensure its extended operation at a required quality. Required mechanisms to meet requirements. One of the mechanism is to use the multi-hop wireless communication. While wireless communication will be a core technique, a direct communication between a sender and receiver is faced with limitations. In particular, communication over long distances is only possible using high transmission power. The use of intermediate nodes as relays can reduce the total required power. Hence, for many forms of wireless sensor networks, so-called multi-hop communication will be a necessary ingredient. So that mechanism that can be used to meet the requirement of the wireless sensor network. Next is energy efficient operation. The energy is required for communication as well as for computation, for sensing and for actuating. To support long lifetimes, energy efficient operation is a key technique. Options to look into include energy efficient data transport between two nodes, or more importantly, the energy efficient determination of a requested information. But also non-homogeneous energy consumption chances are there that will form hotspot problem. So that is also an issue. So we'll discuss all those hotspot in the later sessions. The third mechanism is the auto configuration. So here the wireless sensor network will have to configure most of its operational parameters autonomously, independent of external configuration, as the sheer number of nodes and simplified deployment will require that capability in most applications. As an example, nodes should be able to determine their geographical positions only using other nodes of the networks. So that is called as the self-localization, self-location. Also, the network should be able to tolerate failing nodes or to integrate new nodes. Okay, auto configuration, that is the mechanism that is required. The next is the collaboration and in-network processing. In some applications, a single sensor is not able to decide whether an event has happened, but several sensors have to collaborate to detect an event, and only the joint data of many sensors provides enough information. Information is processed in the network itself in various forms to achieve this collaboration, as opposed to having every node transmit all data to an external network and process it at the edge of the network. Next is data centric networking. Traditional communication networks are typically centered around the transfer of data between two specific devices, each equipped with one network address. The operation of such network is thus address-centric. In a WSN, where nodes are typically deployed redundantly to protect against node failures or to compensate for the low quality of a single node's actual sensing equipment, the identity of the particular node supplying data becomes irrelevant. What is important are the answers and values themselves, not which node has provided them. Hence, switching from an address centric to data centric is essential in wireless sensor network, and it also improves the efficiency. The next case is the locality. Rather a design guideline than a proper mechanism, the principle of locality will have to embrace extensively to ensure, in particular, scalability. Nodes which are very limited in resources like memory should attempt to limit the state that they accumulate during protocol processing to only information about their direct neighbors. The hope is that this will allow the network to scale to large number of nodes without having to rely on powerful processing at each single node. How to combine the locality principle with efficient protocol designs is still an open research topic. The next case is exploit trade-offs. Similar to the locality principle, wireless sensor networks will have to rely to a large degree on exploiting various inherent trade-offs between mutually contradictory goals, both during system design or protocol design and at runtime. Examples for such trade-offs have been mentioned already. Okay, higher energy expenditure allows a higher result accuracy or a longer lifetime of the entire network, trade-offs against lifetime of individual nodes. Another important trade-off is node density. Depending on application, deployment and node failures at runtime, the density of the network can change considerably. The protocols will have to handle very different situations, possibly present at different places of a single network. So these are all the required mechanisms to meet requirements, characteristic requirements for wireless sensor networks. The next topic is enabling technologies for wireless sensor networks. So the first we consider the miniaturization of the chip size, the sensor size, depending on the application requirement. Some applications they require very small size sensors. For extreme vision, we can create the smart dust. So that will also sense some information, uh, what is given to perform to that small dust, what is the task that will be given to the smart dust, that will provide the information to the sync. And another thing is cost reduction, that is also we need to consider. in wireless communication, we need to use the simple microcontrollers, sensors, batteries. The cost must be lesser. Third enabling technology is energy scavenging. So here the batteries are limited energy. So if the battery that has drained out, so the sensor that will be not useful. So to overcome that, so it is essential to recharge the batteries. Several different techniques we can use to recharge the batteries, like we can use the light energy, we can use the vibration. This is still in the research topic. This is energy scaling technique. So this is about the first session, and I obtained the content from this is the textbook, Protocol and Architectures for Wireless Sensor Networks. And thank you.